In this video, we're going to be talking about Charles' law and Gay-Lussac's law. This is gas law number 2 and 3 within our series. Okay, so let's start with Charles' law. Charles' law goes along with specific set parameters as well as Boyle's law did. In this certain law, we go along with the parameter in the fact that the pressure is going to stay at constant, whereas Boyle's law, the constant was the temperature. Now, the involved variables here are now volume and temperature for Charles' law. And as you can see in the read on the statement, the volume of a gas increases as the temperature of the gas increases, and the volume decreases when the temperature decreases. Okay, now we're talking about two different statements here, but they are talking about the same concept here. When the temperature of the gas increases, the volume of the gas also increases. And when the temperature decreases, the volume also decreases. Now we're talking about a relationship in which these two variables are moving in the same direction. When one increases, the other also increases, and when one decreases, the other also decreases. When we're talking about two variables that are moving in the same direction of change, then we call this specific relationship between the two variables as directly proportionate. So we can summarize Charles' law as at constant temperature, constant pressure, volume and temperature are going to be directly proportionate. Okay? This gives us our Charles' law equation of V1 over T1 equals V2 over T2. All right? Now we can actually apply this out into a graph. When we graph this out, we will end up with inevitably a graph that has a straight linear line, and with the axis of volume as our y-axis and our temperature as our x-axis. All right. Generally speaking, that is the specific trend that we'll be noticing for all of our equations here. Okay. Now, as we move on to our next slide, this is a diagram example that shows the relationship between this in a real life or a diagram example. So if we look at these two pistons right here, we're talking about pressure staying at constant, which means that there are no extra pressure exerted onto the lid of this container that we are seeing. Now, at this point, we have to understand that if the atmosphere is staying at 1 atmosphere, is that the internal pressure that is pushing up is also at 1 atmosphere in order to keep that lid at a steady same place and keeping the volume constant within this range. Now, if you were to heat this sample up to 400 Kelvin, from 200 Kelvin to 400 Kelvin, now we're talking about gas particles within this container that are being heated up. And when gas molecules and particles are heated up, they tend to move faster, which is directly correlated within the kinetic energy, which then are colliding constantly against these containers or the sides of the containers. Now, when these gas molecules are bouncing around, all around these wall containers, now the internal pressure increases. All right. Now, if the external pressure that we are keeping at constant is remaining the same and the internal pressure is greater than the external pressure, that means that the lid is going to be pushed up, all right, and then up to a point where it then is able to maintain that 1 atmospheric pressure so that the volume increases to the point where the collisions are a lot similar to that of when it started, which results in the volume increasing. Okay? Now, a prime example that you can see this in real life is when in the wintertime, when we're talking about car tires. All right, when you wake up in the morning and go to start your car. In the evenings, you'll notice that your car tends to have that right pressure within those tires, but then when the temperature cools down, you will slightly notice that your car tire is slightly deflated, and this is due to the temperature dropping and the phenomena from Charles' law. When temperature drops, the volume naturally decreases. This is one of the main reasons and common reasons for your car tire or your car telling you in the wintertime that it says low tire pressure. Okay, and this is because of Charles' law. All right, now we're going to look and focus a little bit more on how to identify word problems. There are simple steps in order to make these word problems simple. When you're reading them, first, the easiest way to be able to identify what you're dealing with is identify those numbers and units that you can easily spot in these questions. So over here in this specific question, a bubble of air trapped in a pool of water has a volume of 1.20 liters at 24 degrees Celsius. Calculate the temperature in Kelvin of the air bubble when the volume became 1.26 liters. All right, so far right here, we can spot three numbers here. We know that there's 1.20 liters, 24 degrees Celsius, and 1.26 liters. From here, we can easily identify that these are the numbers that are involved, and then we have to figure out what does the question want us to find. In this specific one, it asks to find the temperature. Okay, so here, from now on, all we need to do is identify each of these as variables. We know that we're starting this. Since it has a unit of liters, this is my volume, and since that's my initial, that's my V1. Celsius, 24 Celsius, that is my temperature, and that is my starting, so we can easily identify these. Temperature in Kelvin that we're trying to finalize is going to be T2, and volume became 1.26 liter, that is my final volume. Just like this, you should be able to easily identify these variables from looking at the units and understanding what they're associated with. All right, so then easily, nicely putting it into a nice summary here, we put it in a list, and then looking upon this, we understand that V and T are the only variables that are involved, and the only equation we have learned or gone over so far that involves these two variables are Charles' law, which we can easily, safely say that this is the equation we're going to use. All we need to do now is plug the values into their respective variables. So V1 goes in where V1 belongs. Now T1 should go where T1 is, but you must remember that most gas laws are unit dependent, and we have to use specific units. In terms of temperature, we would like to use Kelvin temperature, so we must convert that into Kelvin, which you add 273 degrees. Then you can plug that Kelvin temperature in. Okay, and then we can plug in our V2, and our unknown temperature is, I put it as a variable of A. Okay, from here, all we need to do is cross multiply. So these result into this equation, and you just need to do that cross multiplication, which ends up with giving A as 311.85 Kelvin. Okay, you'll notice that the volume went from 1.2 to 1.26, so it increased, which means the temperature A must be higher than 297 Kelvin, which 311.85, it satisfies that law and makes sense for us as an answer. Alright, moving on to our next gas law. Our third gas law within our series is Gay-Lussac's law. Gay-Lussac's law deals with the same pattern of having a constant and dealing with variables. If you have noticed in Boyle's law, temperature was a constant. Charles' law, pressure was constant. The only variable we haven't touched as a constant now is volume. So you can easily guess that Gay-Lussac's law is going to deal with volume as its constant. All right. Now at a state of constant volume, this law states that when the temperature increases, the pressure of the gas will also increase as well as when the temperature of the gas decreases, the pressure of the gas will also decrease. Notice that same trend like Charles' law. When one variable moves up or increases, the other variable increases as well. These types of relationship we can easily categorize as a directly proportionate relationship. So we can state that pressure and temperature are directly proportional at constant volume. This then goes into our Gay-Lussac's law equation, which is P1 over T1 equals P2 over T2. All right. You'll notice that typically fractions are representative of direct proportionality. All right, when the variables are in a constant fraction. All right. This then we can easily predict how the graph of Gay-Lussac's law is going to look like. The fact that it is directly proportionate, it tells us that it is going to be a linear. All right. Now we've gone through three laws and three different graphs. Boyle's law, you'll notice that it had a very unique graph that was inversely proportionate. All right, you'll note that the easy way to identify these axes are from their equation. The variables become their axis. And then we have Charles' law, which has a similar graph or exact same graph as Gay-Lussac's law. But in this case, Charles' law has the variables of V and T as their axes. And then Gay-Lussac's law, we have pressure and temperature as their axis, which is an easy way to spot which graph represents which law. All right? Okay. And then we're moving on into this example of a diagram. You'll notice that if you're wanting to keep the volume the same, and when you increase temperature, remember what I talked about, the gas molecules wanting to move faster the more it's heated. All right, the faster it moves means the internal pressure is increasing. But if we want to keep the volume the same, that means the external pressure has to increase as well. All right, so that is why you'll note that the pressure change and increase will also be directly proportionate with the temperature change. This Gay-Lussac's law is used in our everyday lives recently. Everybody who has been buying pressure cookers, this Gay-Lussac's law is the prime example on how it works within pressure cookers. Right, keeping that volume in a tight sealed container and raising the temperature raises the pressure as well. This is why you're able to cook your food a lot faster and a lot more efficiently compared to trying to cook something in an oven. Okay. So this is Gay-Lussac's law in the representation of this diagram. Now let's look at another analyzing question. Like I talked about prior, a tank of nitrogen gas has a temperature of 273 Kelvin and a pressure of 330 atmosphere. Assuming constant volume, if the temperature rises to 293 Kelvin, what will the resulting pressure be? Well, again, easy way, pick out those numbers. 273 Kelvin, 3.30 atmospheres, 293 Kelvin. Then figure out what the question is wanting you to figure out. What will the resulting pressure be? Then easily identify each variable. This is your starting point. If you read, this is more of an English part, right? Analyzing this. This is my temperature, T1. This is my pressure, this is my P1. And then the secondary part here, our final, is my T2. And then my variable unknown is my P2. All right. Again, listed out in a pattern. When we list this out, you'll understand that we've gone through three equations. P1 V1 equals P2 V2. We have V1 over T1 equals V2 over T2. We also have our third Gay-Lussac's law. P1 over T1 equals P2 over T2. Okay. Now, the only variables that are involved are P's and T's. This one has P but does not have T. This one has T, does not have P. This one's the only one that satisfies these puzzle pieces within these equations, which means the only satisfactory equation to use here is our Gay-Lussac's law. And then we can just plug in our values from what we've analyzed, and then all we need to do is a simple algebraic question solving and solving for that unknown A or X or whatever you decide your unknown symbol to be. And then when we do that out, simply cross multiply, and then in this case, just multiply 293 Kelvin on each side. You should result with 3.54 atmospheres. Hopefully this summarizes these three laws that we just went over, and this helps you guys. Thank you.